Yet another application of standard deviation is a measure of position called a z-score. As a matter of fact, by definition, a z-score is the number of standard deviations from the mean. For example, if I end up with a z of positive 1.62, then that means that my observation falls at exactly 1.62 standard deviations above the mean. On the other hand, if let's say I have a z-score of 2.03, then my observation will fall at 2.03 standard deviations below the mean. So the number itself represents how many standard deviations. The sign tells me whether the observation falls above the mean or below the mean in a distribution. Generally, a z-score is computed using the following formula. Z is always used to represent z-score. And you usually take some data value, subtract the mean of the data set, and divide by the standard deviation of that data set. This will therefore come in two different forms, one for a population and one for a sample. For a population, if we take some value, some data value, we'll just call that x. In a population, the population mean is mu, the standard deviation is sigma. Therefore, the formula for a population z-score will be z equals x minus mu over sigma. In a sample, similar, still z, we're still taking some value x, some data value, but we're subtracting the sample mean, which is x bar, and we're dividing by the sample standard deviation, which is s. So this would be the formula for a sample z-score. That being said, we tend to use z-scores mostly in populations, at least in this course. So the overwhelming grand majority of problems that you're going to see are going to be in the highlighted portion here. It's also the formula most commonly seen in anything you look up in statistics related to z-scores, which is z equals x minus mu over sigma. So concentrate most of your understanding and your knowledge to this subject matter with that highlighted formula. So just returning to the focus of this section, which is called measures of position. We tend to use z-scores as a way to locate where observations fall in a data set. So that begs the question, when would a z-score be useful in a statistical application? This example should help students understand that. So as you previously learned that SAT scores have a symmetric and bell-shaped distribution with a mean of 1050 and a standard deviation of 210. So remember, we tackled this problem with the empirical rule previously in notes and video. Students in high school also have the option of taking another standardized test called the ACTs, which are normally distributed but with a mean of 21 and a standard deviation of 5. Turns out that some students take SATs and some take the ACTs. It's just actually a personal choice. So they are two different standardized tests, and you can see that they have much different means and standard deviations. But what if we wanted to actually compare scores from someone that takes the SATs and the ACTs? That wouldn't be very easy, given that one mean is 1050 and the other one is 21. That is some vastly different scale right there that we have to somehow figure out in terms of comparing the two to one another. So how do we do that? Believe it or not, we can use z-scores. Okay, so the first question here says, suppose that Jane scores a 1370 on the SATs. Find and interpret her z-score. Okay, so just note that these distributions that are listed in here are from the population of people that take the SATs and the ACTs. So therefore, we are using the highlighted formula over there in order to do this particular problem. So we just need to find Jane's z-score. So that's what we're going to do. So z-scores are always our, whatever our data value we're trying to standardize or find the z-score for, subtract the population mean and divide by the population standard deviation. Well, what is Jane's score? It is 1370. So therefore, in order to turn it into a z-score, I have to subtract the mean of the SATs, which is 1050, and I have to divide by the standard deviation of the SATs, which is 210. If I do this math, I'm going to get 1.52. Now note, we tend to round z-scores to 2 decimal places. We're pretty much going to follow with that as we go through the course, just a little tidbit. Okay, so what does this 1.52 actually mean? Well, if you look at it closely, first of all, it is positive. We did the value that we tried to convert here, 1370, this number right here, was larger than the mean, hence creating a positive number. So what does that mean? It means that Jane scored at 1.52 standard deviations above the mean. So 1.52 is the distance from the mean, and above is because we have a positive z-score. Okay, let's move on to B. So John scores a 28 on the ACTs. Find and interpret his z-score. So a completely different distribution, obviously. We're looking at a mean of 21 and a standard deviation of 5 this time. So if we're doing this z-score, we're going to take his score on the ACTs. We're going to subtract the mean of the ACTs and divide by the standard deviation of it. If we put this into the calculator, we're going to get, again, a positive, because this value is bigger over here, 1.40. Okay, so what does this mean? Well, this means that John scored at 1.40 standard deviations, again, above the mean. So the reality is that both of these students, or whoever who's taking these SATs and SAT tests, actually performed quite well. They scored above the mean, about 1 and so forth, half, 4 standard deviations above it, actually. Okay, so what is the key? Well, C kind of sheds light on it. So based on the results from A and B, did Jane or John perform better on the respective standardized test? Okay, there's a good chance that if I just came to a random person and said, Jane has a 1370 on the SATs, John has a 28 on the ACTs, who performed better? Maybe the most lightning-focused mathematician will be able to tell you, but the reality is those scores relevant to their, or respect to their actual test, that's very challenging to know which one of those students did better. So we actually now know who did better because the z-scores have told us the position of their scores. Whereas Jane has a position of 1.52 standard deviations above the mean, John has 1.40. Clearly, Jane is higher in terms of her position, which means she scored better on the SATs than John did on the ACTs. That is basically what the important part down here is that Jane is essentially scoring better than John on the respective tests. This is what the focus of a z-score is. That's why we use it. It's a great way to measure position in a data set, specifically one that is symmetric and bell-shaped.